Hello, everyone. So a lot of you have known about NVIDIA for a while, but as a gaming company. And recently we've changed our byline. If you've heard any talks from our CEO, he calls us the AI computing company now. We've been around for more than 20 years. We've got a little over 10,000 employees now. It keeps growing quicker and quicker. But we're known for computing on GPUs, computer graphics especially, and artificial intelligence. I'm going to talk about more mundane things, databases, and using data to drive more down-to-earth businesses, right? So the big thing these days is we have so much data. We have a deluge of data coming in. And we used to think about this as a bad thing, that we just couldn't handle the data. It was too big to compute with. It was too big to analyze. And as we're getting better tools and better hardware, we're now able to actually extract value out of this. And we see the data stream as a value add. So we want more data, and we want to be able to process it faster. And as we go through this, we see the same kind of waves of innovation coming along. And then the next wave we're calling the algorithmic business. That's what Gartner calls it anyway. Coming with predictive analytics, prescriptive analytics, machine learning, and cognitive computing, or AI, depending upon who you listen to. These analytics use cases are everywhere, right? We can see them in almost every industry. We can see them from top to bottom, from early education in kindergarten all the way through graduate school out into the world of packaged goods, life sciences, certainly oil and gas, automotive. All these things are impacted immediately and will be more impacted in the coming years as the power to extract value becomes greater and greater. So why are GPUs so special here? Really, the bottom line is we are still seeing this exponential growth curve using GPUs of accelerating every year by a factor of 2 or more that we're not getting from CPUs anymore. So I can write a code on a GPU and expect to get twice the performance in 2 years. And if I do that on the CPU, I'm going to have about 10% more performance in 2 years. That's a big deal. And it's not just about raw compute anymore. A lot of the cost of a program is data movement. And so the key is data bandwidth. How fast can you scan through memory? How fast can I read memory? And the bandwidth available on the GPU is, again, just pulling away in this exponential curve. And for a lot of these problems, especially sparse problems that I work on, it's all about the bandwidth. You do very little compute for the bytes that you access. It's about moving the data. That's the entire cost of the problem. So there's been existing, what do we do today for these big data sets, right? We can try sampling. We can try extracting a subset of the data, analyzing some small percentage. But that's going to miss the big picture. You're going to miss the long tail events. You're going to miss the low probability events that you're going to not see in your sample. We're going to try aggregation. You can try lumping, lots of events together into one meta event, but that's going to lose accuracy. You're going to miss the high frequency wiggles. You're going to miss the signals that you could have seen. And then just the cost is getting bigger and bigger as you have to build more data center space. You have to add more cores to your system to keep getting performance. And this, you're spending more money on switches and racks than you're spending on compute and bandwidth. So these are things that we can stop doing now. We can actually have an answer that will scale. And I'll talk about the GPU compute model, how we bring in GPUs into an existing framework, say Hadoop or something like Spark, and we can, I'll show you 2 different models of compute clusters or analytics clusters. This is a basic workflow saying for the accelerated digital data stream, we have several things I'm going to talk about coming up. We have Kinetica, which is an in-memory accelerated database, MapD, another SQL database in memory, BlazingDB, Blaze graph is about graph data. I'm going to talk a bit about graph data problems. And graphistry is all about visualization of very large data sets. All of these take advantage of the GPU's fast memory bandwidth. And they all integrate back to Spark and the existing HDFS Hadoop data lakes that are already out there. So I mentioned, if you have the standard storage thing going on, this may be what you're dealing with today. And as you go forward, you can see basically all the green areas are places where you can accelerate with GPUs. So from the data storage layer and everything beyond that, the ETL practice, the actual database itself, training of machine learning systems and neural networks, inference, actually running the trained networks in say real time or at the edge of a network, and then visualizing what comes out of those. All of those can be helped with GPUs. So let's go into the three stages here: analyze, visualize, and AI accelerate. All of these are key things that are going to happen in the data center on GPUs. So we can do 10 to 100x faster data processing. This comes back to the memory speed, the computational speed, so you can actually crunch your numbers faster. You can see a result in real time instead of moving the data to another system, running a transformation on it, throwing it into Tableau or some visualization package that's separate from your analytics. You can have visualization that runs integrated with the analytics in place on the GPU. So you can see more data faster, you can answer more questions in the same amount of time that it would have taken you just to move the data to another system. And then getting to acceleration, new algorithms that will let you do things that weren't possible before because we didn't have the computational power to train a network, say, or to run 1 billion rows of data and run a query in less than 1 second, right? I can do that now with GPUs. I can actually query in less than a second over 1 billion rows of data. And that goes back to extracting more value out of the data I have. So here's one example is predicting the weather. From a basic weather forecast and history, I can predict power usage of a small town in this case on the left. On the right, I can predict loan behavior. So if I have a large portfolio, this is from the financial industry, they put together a model of paying off debt. So for a given mortgage pool, they want to predict what's the rate of early payment. And so using the new model trained from existing data, the blue model is the new one, that really gives you a better match to the actual outcome this versus the red. The red is a existing linear regression model they'd been using before. So you can see you can get much better quality predictions by bringing in more data. And this is another example. This is this now become famous, but this is a power usage of a data center predicted by a machine learning system that took in the time of day, the programs running on the data center stack, and the temperature outside. And those inputs, using those inputs alone, it was able to get a really good fit. This is like a 95% accurate fit to the actual power usage. And so what you ultimately come down to is GPUs give you an opportunity to do a new thing. Instead of buying more and more racks and more switches and burning more power, we can do the same things we were doing and now new things that we couldn't do before in much less footprint. So we're talking about one rack that's able to replace dozens of racks for certain tasks. And here's some examples. So we were talking about, as our norm, we're talking about one rack of GPUs, so 12 nodes with 8 GPUs per node in one rack, and this would consume 38 kilowatts of power. And to do the same amount of work that one rack would do, If you're doing quantum physics, for example, this may not interest you guys, but there's a lot of people doing quantum physics out there. I would need to have 8 racks, and that would consume 186 kilowatts. If I would need to do weather prediction, again, that's a big problem. If I want to do cafe, say learning deep neural networks, now we're talking 1 rack of GPUs can replace 84 racks of dual CPU, just vanilla boxes, right? So I've got, and the racks I'm replacing are not, they're really dense racks. So they're 36 nodes with dual cores per node of 12 cores per socket. Those are the vanilla off-the-shelf boxes I can get today from Dell, for example. That's what I'm comparing against. And there's one more example. I've got an updated slide I'll add into the stack here where reservoir simulation comes in. For reservoir simulation, it's 14 racks. So for that one particular problem, we have a good data point. Let's talk about, the node I was talking about was our DGX node. So DGX1 is an 8 GPU box. It's 3 U's thick, and it's designed for these new analytics problems. It's designed to run databases. It's designed to run deep learning. It's designed to do accelerated visualization. And so it's part of the accelerated data center we've been talking about. An application that's really interesting here is how do I apply this to a reservoir engineering end-to-end program? If I start from cores, how do I help analyze cores to get geological layers, and then upscale those layers to get a reservoir model, and I can run some forecasting. But then, usually I've got to do a loop. I've got to go back and history match. So where do we come in? How do GPUs apply in this case, right? So typically you start at the level of microscopic thin sections, a poor scale model of a core you can get with an MRI machine these days. And then you can start matching that at a higher scale to fluid flow properties, right? So you can start tracking how actual rocks flow and train models of the rock properties from cell level data to actual field level behaviors. And applying this to new wells or proposed wells, you can build a predictive model that will construct from nearby neighbors what's the most likely distribution of properties at a new location. Let's see. So here's an example of what, if you do that, someone has done that already, and the fits you get are actually pretty good. You can actually predict with good accuracy. This is about, some of these are 57, 58, one of them is 60 R-squared factors, right? So these are not spot on like the 90% one was, but that's way better than, I used to have to guess basically if I didn't already have a core sample. A new uncored location, getting 50% correct is pretty good. And now I can go in and close the loop. I can start saying, let's do a prediction model based on real data and a much tighter range of physical properties from the core samples I've got. And I don't have to pay for the whole taking it to a lab, wait a week for the lab to run. I can run my model based on my core sample and a scan that takes a few minutes. I can then plug that into my reservoir simulator. My reservoir simulator runs 10 times faster. So I can go around this loop many more times and reduce the risk and reduce the uncertainty of what I'm going to predict in the future and make better decisions. Okay. This is an example of what the MRI scan will give you. You can just plug in a volume directly into machine learning, and it will run a 3D, similar to an image recognition. You're recognizing volume behaviors. Instead of recognizing flat pictures, you're recognizing where's the void space, how is the void space connected. And from that, you can directly predict porosity and permeability and even capillary pressure from just a rock sample. Okay. And this is, the workflow that goes through stacking these up from a poor scale, simple sample to many samples to getting a distribution and then applying that to a field scale to get something I can plug into a reservoir simulator. So that's the loop we use in the machine learning phase. Okay, so what's new? Why is all this possible now? There's three things that came together that Wired magazine called out. The first thing is we have data. We have a lot of data that we didn't have previously. We have better algorithms. We know how to train networks. We know how to train decision trees now. We have random forests. We have boosted forests. We have all these better algorithms that can learn effectively from the data. And we have the power to crunch the numbers, to actually solve these models that require billions of calculations before they give you a useful answer. And when all three of these are coming together, we can solve problems that were just impossible before. So this is another example. It's the same thing I showed before, but if you shortcut going through the history matching, if you can reduce your risk enough to do this in one shot and not have to loop back, I can reduce my cost, I can improve my hit rate, and I can drill fewer wells for more value. Okay, I'm going to shift gears at this point. I'm going to talk about something that is very fundamental to management of data. So graph data, and in particular, graph databases and the management of graph data. So I see graphs as very closely related to any kind of data. So any kind of data is going to talk about an entity or an item that's of interest. And then I'm going to call those the vertices of my graph. Anytime I have a name, I can attach that to my entity. Now it's got a label. I can talk about one-to-one relationships between entities. Those are just simple edges. I can talk about n-area relationships, so many-to-one. Those are, in mathematics, are called hypergraph edges, but they're really just collections of nodes of interest. And then I can put labels on those relationships. So now I can talk about when did someone first meet another person? When did someone actually have their first business transaction? When was the well drilled? Who was the guy in charge of drilling the well? Who was the guy who was responsible for logging the data that came out of that well? And so we're putting together a new package called NVGraph, which is focused on dealing with graph data, dealing with the kind of data that is all about relationships and reducing the cost to other people who want to use this data. We provide out-of-the-box GPU-optimized algorithms, and we'll provide standard formats for readers and writers, so you can easily get the data in, you can crunch, do searches, you can do extraction of interesting bits of data, and then keep the performance constantly improving on this exponential curve that GPUs are on still. So this is a motivational slide. This is why do we even, what's the potential for doing GPU computation on graphs? So one of the standard benchmarks these days is doing something called PageRank, which was made famous by Google. PageRank was the basis for their first web search engine. And now we can run PageRank on 1.5 billion edges, the Twitter data set. So the list of all followers and all tweeters on Twitter up to the year about 2013, and then they stopped giving out the data set. But this has become the benchmark for PageRank. Can you run a PageRank over this very large graph, and how many, basically how many iterations can you do in 1 second? Or how many seconds does it take to do one iteration? It's just the inverse of that. But so we did our best on this with a P100 GPU. We can load the data. All the data fits on one GPU. That's one remarkable thing, is that this entire 1 billion edge data set fits on a single GPU, and we can run it in about 1/3 of a second per iteration, or 3 iterations per second. For this 1 billion edge graph, which is about a factor of 3 faster than what you can do with the top-end GraphMat package written by Intel and on dual socket 12 core Xeons. And also, there's applications outside of PageRank. So if you want to do things like finding shortest paths, finding connected components, those are things we do with the same algorithm that balances the load across the GPU. This is different, a fundamentally different problem than what we were doing with sparse linear algebra. The issue is load balancing. So when you have a known matrix for a PDE or a finite element solver, you'll see there's a regular pattern of non-zeros, and you can fix that pattern and balance that across the GPU very easily. With graphs, basically there's no way to predict the connectivity pattern ahead of time. And generally, if you're dealing with social network graphs, let me back up a little bit. With social network graphs, they have this property called power law distribution, which means some of the vertices, on average, the average is about 4 to 5 connections per vertex. But some of them have 100,000. And if you can't predict which ones have 100,000, it's very hard to balance out 4 against 100,000 evenly across the threads on a GPU. So what we created was an automatic load balancing system to solve this problem, to do the multiplications and adds balanced independent of the sparsity pattern. And that gives us a 7.5x speed up on the same hardware. So algorithms really matter, and this is a graph algorithm that can solve the problems that the existing sparse linear algebra just can't do very efficiently. This is another fundamental thing that we're doing in the graph world. This is just an abstract algebra object called a semi-ring, and it's basically a matrix vector multiply, except you're changing out what the plus and the times operator in your matrix vector multiply with other operators. So as long as they have the same basic behavior, they have an identity, they have a null, and they can do distribution and associative behavior, it's a valid semi-ring. So there's lots of things other than plus and times that work. For example, we have a min and plus. If I replace the plus with minimum and I replace times with plus, that's a valid semi-ring. And that turns out to give me exactly the shortest path answer. If I iterate this on a given graph, I'll get the shortest path from one vertex to all other vertices. And if I do a max min, I can get the algorithm for widest path. So what's the widest path that connects two vertices together? Where if I was going to move material, right, I want to go on the widest path, have the most capacity. Or Boolean, this would just detect are they connected or not. So realistically, graphs are quite complicated. They follow this thing called a property graph, where I have different types of nodes, I've got different types of labels, and I want to mix them all together into one big mishmash, like a data lake of connected data. So now the problem becomes, how do I find what I want out of this data lake? It's all in there, but how do I find the stuff that's interesting? And that's something we call subgraph extraction. I've got an explicit, very large graph of all my data, connecting all my bits together of who owns what, who did what when, what well was drilled when. And now I can pick out just the wells. I can pick out just the production data with GPU acceleration in NVGraph. So this is something we spent some time to make sure this was very efficient, because this happens a lot in real-world data sets. And in the future, we're adding much more interesting things, like the ability to partition very large graphs and do them in parallel across multiple nodes or multiple GPUs. We can find tightly connected communities of nodes. So this is good, for example, finding similar behaviors in a population. Say, what were the number of fractures I got on different wells across this county, right? I can cluster them together and find out which ones behave the closest to each other. I can find BFS is a breadth first search. This is an optimization that allows me to do faster searches to find relationships that may not be obvious in a graph. So if I have data here, I want to know who has the data for the well, 2 miles that way, or I want to find out who's the operator and who drilled it and who did the final sign-off on that well. Well, that's quite a bit of steps away from where I am now, but with breadth first search, we could do a quick search through a whole data lake and connect these things together. And then graph contraction. This is something that I think is very powerful. The idea is I've got a really complicated graph with lots of pieces running around, but I can't see it all. I can't see those connections because there's just too much data. So graph contraction is a concept of, why don't I create a miniaturized version of that graph with fewer nodes? Maybe groups of nodes are collapsed down to one node, but I want to keep the connectivity. So if there was any connection between those groups, keep an edge in the new graph. And so I can build up a hierarchy of simpler and simpler models until I get to a level where I can understand what's going on and keep the ability to zoom in later on interesting parts. I can say, oh, look, all of these things are connected to these things. What's happening over here? Okay, I zoom in, I see more detail. That lets me answer more questions, and then I can proceed up and down through a very big data set without getting swamped in too much data. And this is something that comes up a lot too. So we're bringing in the package called cuStinger. This was designed by Oded Green, and he talked about it in 2016. The idea is, what if I want to track events that are very ephemeral? So things like network connections on an internet or database transactions, right? These things are things that happen quickly. They're important, but you want to be able to read them in, do some quick computation on it, and forget about it. So this is a dynamic graph where I want maybe the entities that are interacting with each other are not changing very quickly, but the interactions between them are changing very quickly, say nanosecond scales. So this is used right now in cybersecurity. So if you want to secure a network and be sure of what's happening on your network, you can record all that activity into a dynamic graph and see how the packets are moving over time, where you get bursts of traffic, where you get DOS attacks, where you have an outside flood coming into one node. And this is also really useful for time series. So I can load time series in, analyze time series, and then move on to the next problem. Okay, just a little bit of background. So the partitioning and clustering I mentioned earlier, they seem like very different problems, right? Cutting a graph apart and then finding pieces that go together seem like different things, but really we do it the same way. We use the same pipeline of computation inside of NVGraph. It boils down to these 4 steps, that we take the graph you're interested in and we build a matrix version of it, spiced up with some special modifications. Say it's a Laplacian of the graph, or it may be we add extra values into it to make it match the problem we're on. But that's just adding up ones and zeros. And then we run an eigenvalue solver. So this is something from linear algebra. You can extract the biggest eigenvalues and their associated eigenvectors. And then you run k-means clustering across those vectors. And what that does is it brings together components that are close in the spectrum. They behave similarly in the connectivity strength of the graph. So if I use just a modified matrix, I can either get a partition that is strongly connected within itself but easy to break apart, or I can say I want the strongest possible connection within this and I don't care what I break apart. Both of those are solved exactly the same way, just by changing the matrix a little bit. So we get 2 problems for the price of 1 with the same machinery. I mentioned k-means clustering. This is important just by itself. So k-means is one of the few algorithms that is a truly unsupervised learning method. It will, you just give it a big stack of data and you let it go off and find similar clusters that match up somehow, right? Usually a Euclidean space. So our version is based on the matrix gem formulation, which is the fastest routine we have on a GPU. It's the most highly optimized. It does a parallel initialization by picking seed points out of the data at random, but in parallel. So instead of picking 1 point at a time, it picks a population of several hundred points at a time, or usually about half of the number you totally need, and it finishes in 5 or 6 steps. And then we added the ability to detect the best fit number of clusters. This is a big problem with k-means. Typically, you have to tell it how many clusters are in your data. But you don't know that. I mean, if I knew that, I wouldn't have to run the clustering method. So what I've done is added an optimization step that runs a search over several clusters and finds the number of clusters which has the best fit. And then, we have first-class performance because we're running on GPUs, and we're within a factor of 2 of the best k-means out there right now. One example we've done for benchmarking, about 200,000 data points with 18 dimensions each, clustered into 512 clusters, and the runtime is 140 milliseconds. The bottom line I'm getting back to, I mentioned these guys before. I mentioned that we have MapD, Kinetica, BlazeGraph. All of these have dramatic improvements in performance and very, very low cost as in terms of hardware for performance numbers, so performance per dollar ultimately. These are the charts that go along. So it's one thing to see a number 100x, but when you see it as a chart, MapD, basically their claim is if it fits on the GPU, we can run any query you want in less than a second. And I can fit 2 billion rows on the GPU these days. Kinetica has claims of being able to run aggregates very, very fast. So this is aggregation time compared to other in-memory systems that use just RAM. So this is tens of times faster than other in-memory databases. BlazeGraph uses, they're running the PageRank problem I mentioned earlier, and they're running it, this is a speed-up chart, so 1,000 times faster than a cluster of, what is this? Yeah, they're comparing against Amazon instances. And then Scream. Scream's claim to fame is they run something that doesn't fit on the GPU. They can accelerate problems with petabytes of data that do not fit on one GPU, but they can run aggregations and simple analytics across very large data sets in one box. So one 2U box replaces an entire Teradata cluster in their analysis. And for other people interested in AWS, we now have a lot of new instances going up on AWS. These have the K80s, and we're talking about updating the nodes with newer GPUs this year. So the existing instances are all 1, 8, and 16 GPUs per node. These are just available on the cloud at any time. So I can load up my data. I can run these Kinetica or MapD out of the box on the cloud. MXNet, all the training systems for neural networks. I'm not talking about neural networks so much today, but those are all very interesting. And ultimately, we have a lot of partner solutions. I'm including after this slide. My talk is basically wrapping up. But after this slide, I've got a lot of slides in the deck for reference material going into more detail on these databases and the analytics packages we have already on GPUs today. So at that point, I will wrap up the talk.